Okay, good morning, everybody. Welcome back to week 3 transport phenomena. Okay, in the week 1, we have discussed the modeling at the different level, and then we have tell you guys about the transport phenomena. So it's covering the momentum transport, the heat transport, and the mass transport, right? And then last week we have start on some of the concepts behind the momentum transport. We have shown what is the molecular momentum transport, and then the convective momentum transport, and then the combined momentum transport, and then we go through all the notations, especially the derivations of the Newton's law of viscosity for the different coordinates, for the cylindrical coordinates, spherical coordinates, and the spherical coordinates. Okay, so we then in order for us to emphasize those concepts, then we go into the example. The first example is the flow of a falling film. So that one is a flow of liquid down an inclined flat plate of length L and with W, basically. So I hope that there is no, if you have a confusions regarding the concepts and the notations, then it's the right time for asking is now. Basically, if not, then we have to go and continue into the last example that we talk with. So this table B1 is something that is important that you will use throughout your derivations, and also in assignment 1 you will deal with this one, the cylindrical coordinates, I think this one. Okay, and then you will connect it back with your postulations and also with your boundary condition. So this table is something that you need to be familiar with. Okay, and then you can get it from your slides, and then if you are wondering where I get those concepts again, you go and look in here into the chapter 1 of your momentum transport, and then our example in here is taken from the chapter 2 of the Bird, Stewart, and Lightfoot, basically the shell momentum balances and velocity distributions in laminar flow. Okay, so the one that we are discussing, the first example, will be the flow of a falling film. So I will not go through the details of this one because I think I have discussed this in my pre-recorded video, and also I have discussed this in my last week drop-in session. Okay, so far everything is good. If you can listen to me, then if you cannot listen to me, then you please raise your hand or get my attention if you have a difficulties in listening to me. Okay, sometimes my line get cut. Now, I will continue with my example. Okay, I will continue with the example in here. So we have derived the integrations, okay, the boundary conditions, the integration, and then the plug-in of the boundary condition. So okay, Saif, you cannot go in, or what? Try again. Oh, okay, let me just text with Saif, and if cannot, you can still get the recording. Okay. Hello, what's up? How are you doing this morning? Everything good with you? Can you hear me? What's up? Okay, good. So we get this the integrations already. Hi, good morning, Evangeline. Just you can type if you can listen to me well, Evangeline. Okay. Just let me know if you can hear me clearly and if everything is good with you, Evangeline. So we integrate this one already, and then we plug in the boundary conditions, right? The boundary conditions, and then we derive this from the Newton's law of viscosity connected with the postulation, right? Okay. I don't know what is this. Just Saif, you try it again. If you cannot, then I'll. Anyway, I'm here. Okay, we'll just wait for you to come in. So after we put in the Newton's law of the viscosity, then we can get the integrations. Okay, the boundary conditions, the Vz and everything in here. So I discuss up to this point. Okay, so by plugging in the boundary conditions at x equals 0, the tau xz is equal 0 is where we get from this the most commonly used boundary conditions for the transfer phenomena. So we have given at three conditions. At the solid fluid interfaces, the fluid velocity equals the velocity with which the solid surface is moving. At the liquid-liquid interfacial plane of constant x, then the velocity and the shear stress will be continuous, okay, on the interface. At the liquid-gas interfacial plane of constant x, the shear transfer components are taken to be 0, basically. Okay, so that will be what the implication for this one is. The first one. The first one is on the top. So if you imagine that you have this, you're talking about the top side of your film, basically in here. So your system is a liquid, okay, and then this one is a fluid. So this is a gas, okay, this is a gas. So you're talking about the interface between the liquid with the gas. Okay, Saif, I think you can go in ready. Is all good, clear? You can hear me clearly, Saif? No? Just let me know. You can type it in there if you can hear me clearly. Okay. So the top, we are talking about the boundary conditions on the top of the film in here. So at the top in here, okay, the shear stress should be equal to 0 because the viscosity of the liquid is much higher than the viscosity of the gas, right? So that one we can put in at x equals 0, tau xz is equal to 0. So your constant is equal to 0. So you get your tau xz. Okay, when I'm talking about this tau xz, that means this is you're talking about this one. Okay, so meaning that the velocity is in the z direction, the momentum is in the z direction, but the momentum transport is in the x direction. Okay, so this is consistent with your pictorial view of your system. So the film is moving down on the z directions, but the transport of the velocity is in the x direction. Okay, so that is very important for you to iterate again in here. So because this is a tensor quality, so I keep on iterating this fact from my last lecture, the drop-in session. Okay, so this tau xz is a linear functions in x, rho g cos beta x. Hello Daniel, I hope you can hear me. You tell me if you can hear me clearly. You just can type in there, or you can give me a. So this x in here is you get rho g cos beta x. So then you draw it again in your system again. So as you can see that on the top you have 0, but as you go down, then in the bottom in here, that will be a rho g cos beta. Okay, rho g cos beta multiplied by your thickness of your film. So your shear stress at the bottom will be rho g cos beta, and then it will be theta in here. So you basically have a linear profile from the top to the bottom. So it's basically reflecting what the mathematical equations that you have in here, right? Once you have this tau xz in here, this profile, then what you will do is you go back and check again in this table again, or in the slides you check in here in appendix B. Okay, for that particular, for this Cartesian coordinate, your tau xz is equal these equations in here, right? And then as you know, in your postulation before, that your velocity in the x direction is 0. Why? Because there is no velocity in this particular direction. You only have the liquid that going down in the z direction. So the velocity is 0. Okay, as a result, this first term in here becomes 0. So you can simplify your tau xz becomes this, right? Then you substitute these equations into these equations in here. Okay, this equation in here. Then after that you integrate this equation. Okay, you integrate these equations in here. Then you inspect the second boundary conditions. What you have inspected is on the top. Then now you inspected what is in the bottom. In the bottom, you have an interface between the liquid with the solid. Okay, so in here, the velocity of the liquid at that particular interface between the liquid with the solid should be equal to the velocity of the solid. Since your plate in here does not move, meaning that your liquid at that particular interface should be not moving as well. So meaning your velocity should be equal to 0. Once you put in that thing, then you will be able to get your second constant. Your second constant is equal to this. Then after you put in your second constant, you will get these particular equations. Now, with these particular equations, you have an x that are basically raised in order of 2. So you will have a parabolic velocity profile that varies from 0 to the maximum on top in here, right? So where the maximum velocity is reaching at this particular point, or that will be at x equal 0. So when you substitute x equals 0 in here, then your velocity max is equal this term in here. Okay. Now, what will be the connections between the velocity and the shear stress? So you notice that at the value where the shear stress is equal 0, the derivative of the velocity in the z direction with respect to x is equal to 0. Okay, at that particular point, your velocity becomes maximum. Okay, so it in your calculus you will know that at some particular equations you can find the maximum velocity. You can find that maximum value of that particular functions if you find the differential and equate that equal to 0. But not every function will be true for this particular particular context. But normally that will be true. Okay, for this particular case, then this will be true. Okay, so now after you go back, you establish your tau xz and then your velocity in the z directions, then you can draw back into your system again. So in the beginning, when you start the systems, you don't know, you don't have a picture, you just have an assumption, you make a postulation so that Vz is a function of x, but you don't know what that, how that Vz varies with x, okay? And then your Vx is equal 0, your Vy equals 0, and then the P is a function of x, right? Now, after you get that two equations sorted out, then you can draw it in here. Go back again to your system and you draw, and you know that it will have this, the velocity has this particular dependence and this shear stress has this particular dependence, right? Once you know that thing, then you have a mental picture of these things. So you can get this maximum velocity is the velocity at x equals 0. Okay, so that Vz max is on the top in here, right? That will be this one. Now, you are talking about the next quantity that you are interested to find is the average velocity over a cross section of the film. So you need to go back into your system again. So if I go back into my systems again in the chapter, I'm sorry guys, I have somebody that basically cutting a tree or something, just my neighbor. So this is outside of my my control. I really cannot do anything with that sound. So you have to bear with me, and I'm sorry with this. So now you go back again into your systems, and instead you check with this particular velocity. You know that this is going in this particular directions, right? This particular direction. But if you go into the 3D of these things, then you imagine that the film is going down like this, and your velocity profile is varies only in this particular direction, only in the x direction, and you want to average it in the area that is perpendicular to the flow. So this you are interested to average the thing with respect to the y, and also with respect to the x, and with respect to the x, and with respect to the y. Okay, because the direction of the velocity is on the z direction, so you are interested to average it on the area that is perpendicular to the flow direction. Okay, that's why you have these terms where you integrate with respect to dy and integrate with respect to the x. Okay, so that you integrate, and then the Vz. This Vz in here, as you know, is a function of x. Okay, now once you integrate this velocity over the cross sections of the film, again, the flow is going in this particular direction, so the area that is perpendicular to the flow directions will be on the y and on the x. That's why only x and y in here come out in this particular integrations in here. Okay, now the definitions of the average is that the velocity you integrate over this particular area divided by the area itself. Okay, now you know that the Vz in here is a function of x, so the dy in here is not related with this Vz and the dx. Okay, because y in here is not a function of x, so we can split this double integral into the two terms in here. So integral of the Vz dx, okay, and then integral of the dy in here. Okay, and likewise for the denominator part in here, you can split it into two terms in here, the x and then the y in here. Okay, the integral of the dy from 0 to w will be equal to w, and then the integral of the 0 to this theta of the dx will be equal to this theta in here. Then you can cancel these things out, so your average velocity in here will be equal to this quantity in here. Okay, now you substitute your Vz in here, the Vz in here, you substitute in here, then you integrate in here. Then you need to know that this particular terms becomes a constant because you integrate in terms of the dx in here. Okay, so this one I think I miss out the dx in here. Okay, I need to put in a dx in here. And then once you do that thing, then you can integrate that. The integration of the constant will be whatever is multiplied by dx. And then this one will be, the integral of this one will be 1/3 of the x. And then you have to increase the order by 1. Okay. Then you continue again. Then you will get that the integral of the Vz dx is equal to this term in here. Okay. Now, once you get this one, then you can establish that this average Vz is equal to this term in here. And then you can do some mathematical manipulations to express this Vz in terms of the maximum velocity. So in this particular term, for example, we can multiply the denominator by 2 and then the denominator by 2. So it will be essentially equal to multiply by 1, right? Then we know that this particular, then we can move in the two term on the denominator into the front, and then we move in the two term in the denominator into the back. Okay, and then we know that this particular term in here is equal to the maximum velocity. So the average velocity is equal to the 2/3 of the maximum velocity. Okay. So once you get the average velocity, average over the cross sections that is perpendicular to the flow directions. Okay, so you average it on using a surface area that is perpendicular to the flow directions. Then that will be 2/3 of your maximum velocity. Note that your maximum velocity is the velocity on the top in here. Okay, the velocity at x equal 0. So this is very important. So based on all these derivations that we do and all the concept that is given, we now know that using these conservation principles, we now know we have a better view of your system, because we are dealing with the microscopic view in here. So you know you can get the velocity profile, you can get the shear stress profile, and you can get the average velocity. Now, what is the thing that is interested if you get the average velocity? Now, once you get the average velocity, then you can get the mass rate of flow. So your mass rate of flow is equal to your average velocity multiplied by the density in here. Okay. You can check the units again. If you multiply the units of this one, for example, this density is normally given in terms of the kilogram per meter cube, for example, then you multiply by the meter per second, and then this will have a unit of meter, and then the meter, then your unit will be kilogram per second. So you need to always check the consistency of your unit. Okay, if you do that thing the same way that you do it for that one, then what you will get is basically this one multiplied by another row. Okay, so that will be simply these terms in here. Okay, and then you can do some mathematical manipulations to express this mass rate of flow in terms of the average velocity. Okay, I make another a note again in here because I have you have two different W. You have a small w and a capital case W. The capital case W in here refers to the width of your systems in here. Okay, that's the width of your plate in here. Okay, whereas this W in here refers to your mass rate of flow. So in order for me to avoid confusions, then I put another note again in here to make it much more clear, because in here I differentiate between the small w with the big W. Okay, then based on these particular equations that you get in here, you can also get your film thickness in terms of your mass rate of flow. So then you will ask me why you are concerned with these things. So for example, in chemical engineering systems, you deal a lot with this kind of particular flow in here, the flow of liquid down inclined flat plane. Okay, so in your unit operations, you can basically, if you want to get the film thickness of your particular systems, okay, if you can find out the viscosity, you can find out the mass rate of flow, you can calculate the mass rate of flow, for example, and you can get the density, you can get the gravity easily, and then you can get, for example, for a particular plate or film width, for example, and then the angle, then you can get the film thickness. You can predict the film thickness from these particular correlations. Okay, or if you can you get the other quantity, then you can also get the mass rate of flow, right? So whatever this is given in here, the derivations given in here, it will connect back to your experiments. So in the old days, when chemical engineering wants to get the density, or the chemical engineer wants to get the viscosity, then they will design an experiment where they have two sets of the parameter. One set of the parameter is known from the experiments and can be calculated from the experimental geometry, and the other set of the parameter is something that is not known, for example, the viscosity. So this is how the chemical engineers calculate the viscosity, is coming from these particular experiments, from the transfer phenomena, from the microscopic level of design, basically. Okay, this will become clear as we go into the next example that I will discuss on Friday, not on today's drop-in session. Okay, in today's drop-in session, I will just finish this example and move on to another example that is a little bit of development of this example. Now, the force per unit area in the z directions on the surface perpendicular to the x direction is basically your shear stress evaluated at x equal theta. So if you go back again to your system, you want to evaluate the force, the shear stress at the bottom of your liquid. Again, for this particular transfer phenomena problem, we took the original coordinate of 0, 0, 0 is from this particular point in here. Okay, we want to inspect the the force that has been applied by the liquid on this particular interface in here, where basically the liquid touches the solid surface. Okay, so that will be what it is in here. And then so how do you do that thing again? Shear stress is operate tangentially, so it's not operating normally. So if you're dealing with the normal pressure surface, a normal force, basically it's whatever you push, and then that will be the force. But in here it's not. It works tangentially. So because that's why it's called a shear stress in here. Okay. So what you need to do is you integrate with respect to the surface area where it operates. So you integrate with respect to the z from 0 until L, and then from 0 until W. So you are dealing with the y and z coordinates in here. Okay. So this y, it comes out in here that you integrate with respect to y and with respect to z. And then in here you inspect it at x equal the theta, because that's the positions where the force basically applies. Okay, at the interface between the liquid with the solid. Now what you need to do is you substitute these things, and then this dvz over dx at x equal this is something that you have defined earlier, so that will be equal to this one. So dvz over dx is equal to this one. Okay, that will be equal to this one in here. Then you plug in the value of the theta. Okay, you plug in the value of the theta in there. Once you plug in the value of the theta in there, then you multiply it by the minus viscosity. Okay, now this particular things in here does not have a connections with the dy and the dz, because this is only a constant after you substitute the theta in there, right? So if there is any correlations between this with this dy and then dz, then it will not be so direct. So you have to integrate with respect to that particular functions. In here it's not. There is no connections between this particular term in here with the dy and then the dz. So you can just integrate this dy separately, the dz separately, okay? And then you will get this particular force. So your force will be equal to the density multiplied by the gravity multiplied by the film thickness multiplied by the length multiplied by the width multiplied by the cos beta. Okay, so up to this particular example, I know that I have been repeating my recording, but this drop-in session has a particular purpose. So the purpose is for you to clear up your doubts from the beginning when I start this particular derivations up to the end in here. So I will stop a little bit in here, and I want to go back to you again and ask you, is there any particular difficulties, anything that you don't really understand when we discuss this particular example? Any step that you don't know? And anything that you are confused with now? It's the right time for you to clarify this. Okay? In essence, your assignment 1 is basically just the application of this particular things. Is the same, except that will be using a cylindrical coordinates. So it has the similar things with what we will discuss in the example 2 and example 3. So in this particular example, we are focusing on the Cartesian coordinates to give a more clear example of how you apply those principles of the how basically you make your postulation, how you connect your postulations with your generalized Newton's law of viscosity that we discussed in this appendix B in here for the different coordinates. Okay. Anybody has any questions? Gladys, Sarina, Tiara, Jonathan, Alvin, Evangeline, Saif, Daniel. Don't be afraid. Come on, seriously, just ask me anything if you have any question, because if you have a difficulties at this particular point, then later on it will be difficult. Anything that you don't know, then you can ask me now. Right? I will not say something like it's a stupid question or something, because no question is stupid. Okay, and the point of the drop-in session is for me to communicate with you, so that you can clear your doubts or any questions. So that's why I've been keep on asking you again whether you have a questions and whether you have a questions. Okay. Okay, if you don't have, then now I will move on into the next one. So let's discuss the example, the next example, that is just a little bit of the same example, but it's just a little bit of the modifications on that particular example. So after we discuss and finish everything, then we want to inspect another example. Okay, so let's say we have the same case. We have a falling film problem, but except this time we have a position-dependent viscosity. So the viscosity will change as a function of x. So meaning that now your velocity at the positions of at this particular positions may be different with this velocity at this particular position, and it may be different with the velocity at this particular position at this particular position. So in the original problem, we assume that all the physical properties are constant. So the velocity is constant, the density is constant, so everything is constant, and it does not change as a function of the position. Okay, so we are basically using a definition of the lump parameter for all those parameters, meaning that nothing change as a function of the position. But in this one, in this particular example, we define a simple, I would say that it's not very simple, but it's quite simple anyway. It's where basically your viscosity is an exponential function of the x. Okay, so at basically when you put in at x equals 0 in here, then that mu will become mu naught. Okay, so this if you get an increasing x, meaning that this value will diminish with the distance. Okay, or you need to go and look back into the shape of the value for this exponential. Okay, so the mu will be rapidly decreases with x, with increase of x, basically. That's why this is negative in exponential term in here, right? So if we assume these things, then it will not be as straightforward as if we just put in this term in here, right? So at this particular term in here, so this will be the same with the boundary conditions. Everything will be the same up to this particular point. The difference will be when we substitute the Newton's law of the viscosity. When we substitute Newton's law of the viscosity, then because this mu is no longer a constant, then you need to, the way that you integrate this thing will not be as simple as when you integrate these things in here, right? So what are the difference? So let's inspect these things in here. So we start with this tau xz rho g cos beta x in here. Now we have this tau xz is equal minus mu dvz over dx. So now we put in this mu is equal to the mu naught exponential minus lx divided by this theta dvz over dx. Then what we need to do essentially is to separate the variables. So we separate the variables of the vz into the left hand side, and all the variables that contains the x on the right hand side. So we are just using a simple analytical steps to split these things. Now we have a bit of difficulties on the right hand side in here because we need to use an integration by parts in here. Okay, so the integration by parts is we just use this particular formula. Integral of u dv is equal uv minus integral v du, right? Then the question is which one we choose as u and which one we choose as a dv. So you guys can find another route for doing these things. I think it will anything that is correct will lead you to the correct answers anyway. So in here I simply take that u is equal x, dv is equal e, l divided by the theta multiplied by x, so that du is equal dx, v is equal this. Okay, I integrate this one in here. Okay, so integral x e L over theta x dx will be equal to u v. So you just multiply this x multiplied by this term in here, which is equal to this one, minus integral dari integral v, this one, du. Okay, then you can integrate these things. You will get these particular terms in here plus constant, right? So if you proceed with this one, then you can put in this constant in front of these things, and then these terms in here will be here. You use the same boundary conditions again. Okay, the same boundary condition is applied in here. Then you will get the constant. Now your velocity profile will have a different dependence. Okay, it will have this particular dependence type in here. Okay, so up to this point, because you have a varying viscosity with the distance. Now the questions that makes it interesting is that how do you recover this particular term from these equations in here, because this will represent a much more general case than these equations in here, than this particular equations in here. Okay, this particular velocity profile is a special case of these equations in here, whereby alpha is equal to 0. Okay, but now you cannot put in alpha in here directly, because if you put in alpha as 0 in here directly, then you will end up with infinite terms in here. You will end up with the infinite terms in here, you will end up with the infinite terms in here, and you will end up with the infinite terms in this particular term. So what are the solutions? The solutions is that you can use you can expand the exponentials in the Taylor series. Okay, that is something that is described also in the appendix C, if I'm not wrong. So you have this expansion of functions in the Taylor series. Okay, and then as you go into your process control later on, you will also get when you linearize your systems, then you can use this so-called Taylor series expansions. Okay, so these are something that you can use in this appendix C2. So what you need to do is you just change this term in here, the exponential term in here, and this exponential term, and express it in terms of the Taylor series. Okay, once you do that thing, and then you do a very careful mathematical derivations, okay, you will be able to recover what I recover in here. Okay, and then once you put in your alpha is equal to 0 at this particular term, then you will recover these things, and this is basically the same with your thing in here. Okay, except in here it's ascertained as the mu, but in here is ascertained as a mu naught. Okay, so what you get from this example, what I want to essentially show in this example is that when you are dealing with the transfer phenomena problem, then all the assumptions that you make in between your steps is very important. And if I give you a problem in this momentum transport, then you need to always inspect the assumptions and then check again the definition that is given in the problem, and make sure that when you integrate and do everything, when you substitute, that you are doing the correct mathematical steps for the derivations. Because sometimes a dependence on the viscosity may create a different way of the processing in terms of the mathematical derivations. Okay, so I think that's pretty much the example that I want to discuss for today. So on the next example, on the next drop-in session, I will go and discuss into the flow through a circular tube. So this will be we are gonna deal with this second example. Okay, so the second example is dealing with this flow through a circular tube. So this will be this particular example in here. Okay, so that will be almost the same with what you do with your assignment, especially the example, the next example, the example 3. Up to this, so I have been discussing this for about 45 minutes now. I don't think I can add on anything that you want me to add on up to this point. No, everything is clear. Everything is clear up to this point. No questions. Gladys, Sarina, Tiara, Jonathan, Alvin, Evangeline, Saif, Daniel, no? Yes, please do so, Tiara, and all of you, please try to start as early as possible with assignment 1, because if you do it on the last week, then that will be very tough. Okay, I've been especially, I mean, when you are trying to get there are 3 questions in that particular problems, and then the second question and the third problem is not as easy as what you think as well. Okay. So I really encourage you to start as early as possible, and if you need any time for you to discuss that problem with me or anything, then again I will not say that any questions is stupid. Is not okay. You can ask me anything that relates with your understanding and anything. Okay, because transfer phenomena is like this. So I'm trying to go down to that level where you can understand. But as I go with the week 6, week 7, and I will not be able to go into the detail. That's why in the beginning I said to you guys that the first 5 to 6 weeks are very important for your understanding. If no, then I think I will just stop the recording, and then I will conclude the sessions. And I hope you have a good lunch, and then tomorrow there will be no drop-in sessions because tomorrow is a public holiday. So we meet again on Friday. Okay, thank you everybody.